Hi, there is so many of you, it's not scary at all. Hi, my name is Tania, and I'm a developer advocate at Microsoft, and I'm going to be talking about something that I'm very passionate about and something that I've been talking about for many, many years. And it's reproducible science, or more like reproducible research. If you are having trouble seeing my slides or you want to revise them later, they're available online already at .url. And everything is CC BY, so you can use remix and modify as you need. And you might be wondering why a developer advocate is talking about research. I'm a recovering researcher. I have a PhD in computational nanomechanics. And while I was doing my PhD, it became obvious to me that I didn't want to go down the traditional academic path of becoming a lecturer, senior lecturer, and professor, but I jumped into a different profession. I'm also now an Alan Turing Institute Industrial Fellow, for those of you that are not based in the UK. This is the National Data Science Institute, and it's formed by a consortium of different universities and industrial partners. I'm also been working as an RSE, or Research Software Engineer, and I'm a current trustee for the RSE Society in the UK. And finally, I'm also an editor for the Journal of Open Source Software, so I have my fingers everywhere. And because of all of this, and because how much I care about reproducible research, I spend a lot of time thinking about the problems that we as researchers or research software engineers face. But I am very aware that thinking about a problem and talking about a problem doesn't solve it. It just makes it bigger or noisier. So I also spend a lot of time helping researchers to make their research more open, more reproducible. And because of my background, I also spend a lot of time working with data scientists to make their machine learning algorithms and all of their machine learning work much more reproducible and transparent, because this is something that I deeply care about and I think everybody should care about. And I want to also highlight that reproducible science or reproducibility is not black and white. It's not just as your science is reproducible or it is not. There is a very long road for us to achieve this ultimate goal of reproducibility. And there are different layers. So if you start doing research or investigating or reading papers, you're going to find out that there are lots of terms thrown around. Things like reproducibility, replicability, explainability, blah. So I'm going to just give a very brief introduction of some of these terms so that we are all on the same page and we understand what I'm going to be talking about. So we're going to be concerned about reproducible science, meaning that we're also going to be focusing on scientific computing for the purpose of this talk. So imagine that you have a research question and you have two people or two independent research labs trying to answer the same question. If they have the same exact data and the same exact analysis or scientific software, they should get to the same result. That seems like a logical thing. So that's reproducibility. That's what reproducible means. If we're talking about, again, the same research questions, and we have the two labs or the two people, but each of them are collecting their own data to answer the same research question, but they're using the same analysis, and they get to the very same answers, that's a replicable study. When we're talking about robust science, that means that you have, again, one single research question that you're trying to answer, and you might have people collecting their data, but they have different analysis. And when I'm talking here about different analysis, doesn't necessarily mean that there are different theories or different algorithms, but things as just using different programming languages like Python or R or Fortran or C++. And if you get to the same result, if you get to the same conclusion or proof or disproof of hypothesis, then you can say that that study is robust. Finally, we have generalizable research, where for the same research question, people collect their own data sets, have their own analysis, and they get to the same answers, to the same results. As you can imagine, these different approaches and these different types of reproducibility or layers of reproducibility have their own challenges of themselves. So for the purpose of this talk, we're going to focus on reproducibility. That is, one research question, same data, same analysis, same results. And also I want to highlight something very important. People often believe that reproducible is exactly the same as open. They're not the same. They go hand in hand, and this is very important, but there are cases in which we're working with very sensitive data, like criminal data or healthcare data or highly identifiable data, and we cannot make that open because reasons, because privacy, because security of the individuals or the systems that we are representing with our models. And I'm going to start with the goodness of science, because it's always nice to start with nice things, have an uplifting talk at the beginning of the day. And when I think about the goodness of science, this picture comes to mind. This is a picture from the 1927 Solvay conference, and you can see there are some of the brightest physics minds in there. They're all together, and you can only imagine the amazing level of conversations that these people were having. You were basically gathering the brightest and most prolific physics minds in a single place for a span of few days. After those days of intense collaboration, conversation, innovation, they would go back to their home institutions, write research papers, and disseminate those ideas to the wider scientific community. And this model is pretty much the model that we're still following. Pretty much the same, a bit changed and adapted to our workflows, but still, the research papers and research publications are the first medium that we have to disseminate our innovation and our ideas to our wider scientific community. But as things change, there has been a lot of events moving research forward. And from World War II and the 1950s, people started realizing that there was a big need to start doing more intensive number crunching. And that's when all of these people that were doing computer science, that had access to compute power, became very well regarded and very well respected members of the scientific community. And this was not only in academic institutions like MIT or Harvard or Oxford, but also in places working around defense or aerospace industries. And this definitely changed completely the game for research. And as computers became more accessible to us, to the community, that even more changed itself. Now everybody has a laptop, everybody has a PC or access to supercomputers or high-performance computers or cloud. And we cannot say anything different, but software and compute has changed the world. And it continues to change it and change the way we conduct research. And in order to investigate and have a feel of how much research is now impacting the different areas of research, the Software Sustainability in the UK conducted a survey a few years ago with researchers in universities that belong to the Russell Group in the UK. For those of you that are not UK-based, these are the most prestigious and wealthier universities in the UK. If you're in the US, you can compare this to the Ivy League universities. In this survey, researchers, well, around 92% of the researchers said that they use some sort of software for their research. Around 70% of the researchers said that it was actually fundamental for their research or for their work, meaning that if they didn't have access to compute or software, that would completely stop or dramatically slow their progress rate. And over half of those respondents said that they developed their own software. Now, these are very significant numbers for the use and adoption of scientific software, but when you run this kind of surveys, there's always the risk of certain bias, because those that are going to be answering these surveys are more than likely the researchers that already care about software. So to do a further analysis, the Software Sustainability Institute had access to ePrints. And we did an analysis of over 6,000 articles published from 31 different UK institutions. And we were looking for terms that would depict the use of scientific software, either directly or indirectly. So we're looking at terms like Python, Fortran, Ruby, modeling, simulations, things of the such. And we observed that over a period of 15 years, the references to scientific software being used in research has increased 10 times or tenfold. So now it doesn't matter if you're doing hard sciences like physics or things in mathematics, humanities, linguistics, you rely on software in a certain manner or other. It doesn't matter if you're writing very complex or sophisticated Python scripts with Dask to do distributed computing, or if you're using Fortran 77 because that's what you were inherited, or if you are using Excel spreadsheets to analyze your genomic data. It's all valuable scientific software. And the fact that we have all of these very wide ranges of data and software literacy in research is something to be amused for or something to be interested about. And I'm going to show an example of scientific computing done right and where it can take us in the areas of innovation. And I'm talking about the Event Horizon Telescope results. This became massively popular earlier this year. It was everywhere. It was on Twitter, on every media, every news. My feed was exploding with this. And it is something to talk about. It's an incredible accomplishment completely fueled by open source scientific software. When we look at those 4 pictures, it's very easy to think, oh, there are 4 blurry circles, and forget about all the incredible amount of work that it has gone to generate them. It's also easy to forget how much information we can actually get from those 4 blurry semicircles. We're not only getting a nice picture, we're getting a complete story of black holes, the matter, and their entire environment around there, and how the universe interacts and forms these very complex and magnificent systems. And it's something to applaud, really, because this research didn't happen over a matter of few months or even a matter of few years. It was a culmination of years and years and years of collaborative effort. It included over 200 different researchers spread across 6 institutions in 18 countries across the 6 continents. And for you to be able to manage that amount of data and that amount of people and resources and come with something so valuable like this, it's a huge accomplishment. But also, this culminated in 6 research papers that were published in April 2019. And if you go and look at the acknowledgements and citations of those papers, you're going to find things like this. All of these open source packages and tools that we all love and use, things like Jupyter, Matplotlib, scikit-learn, all of that, they are there and they're being acknowledged. Because they fueled innovation, they fueled this project, because they were the battery, and people didn't have to spend years again reinventing the wheel. They had to collect their data and build on the shoulders of those others that had spent all time and effort and love making this available. And that's the beauty of our ecosystem. That's the beauty of the scientific Python ecosystem and the Python ecosystem as a whole. What our community builds is building blocks, and we're free to use them and remix them and put them together as we see fit and as our needs demand. That means that we can rely on a set of open tools and open infrastructure to achieve our objectives. And I'm going to put as an example the Jupyter ecosystem and Every time I talk about reproducible research, I talk about the Jupyter ecosystem because it's a stellar example as well of how using open tools and open infrastructure is not only giving you means to achieve something, but it's means to empower an entire community to do better and change for the better. And the best thing of our ecosystem as well is that it doesn't matter if you're trying to do research or science or web development on your laptop or on your works PC, or you have access to your on-premises cluster or the cloud. It all plays nicely, and you can leverage the compute power that you have at the finger of your tips, the tips of your fingers. So you can do more with what you have. And this is all very good. This is all very exciting. Every time I find research that is powered by open source scientific software, I'm very excited. But not everything is good. We have so many hurdles and so many battles still to fight. If you ask the public, if you ask founders and institutions what they want from research, what they expect from researchers, everyone is going to tell you, we want innovation, we want openness, we want collaboration, because those are things that we usually relate with science and research. And when we have examples like the Event Horizon Telescope results, we all applaud how open source fuels this. There was this tweet by the Matplotlib group, and because everybody spotted that the figures were generated using Matplotlib, and it blew up. Twitter was suddenly full of love for Matplotlib, and it finally received all the love that it was due in years and years. But also, there were disappointing news a few days later, not even a few years. Matplotlib applied for a grant, as did many other open source projects, a grant for subsequent funding, or funding for them to make them more sustainable or make critical improvements. And those grants were not approved under the basis of we're not able to measure the impact of these libraries, or the impact is not significant enough. So how can this happen? All of these libraries are the batteries for innovative research that is not only fueling the generation of cosmic pictures, but powering all the machine learning and all of our machine learning systems and apps that we are working with and living on a day-to-day basis. So how can we not measure the impact of these critical packages that are maintained by only a handful? And the truth is, because what we say that we want from academia and what we're actually demanding from academia and research and open science software is fundamentally different. If you're doing research, what you're measured by is, again, the number of papers that you're publishing. And not only the number of papers that you're publishing, but how many people are actually reading them, citing them, and referencing your work. So that is a trade coin that we have in research. So if we were looking at a research cycle, a very simplified, normally start with your research question that you want to answer. And you formulate a hypothesis, you design your experiment, whether it's a physical or a computational one, to prove or disprove that theory. You experiment, you collect data, you analyze the data, and that's a very big loop. And eventually, you reach to a conclusion whether your theory is proved or disproved, and you publish. That's how it works. Like like a 100 feet view of it, probably a 2 kilometers view of it. But because, again, researchers are so currently urged to publish fast and publish in high-impact journals, didn't have time to brush up those things. And those two critical parts where we're doing the analysis collection of data are being treated as black boxes, because we publish, and the paper is the first-class citizen, and my code and my data are second or third-class citizens. So how can research be open and how can it be transparent and reproducible if crucial parts of it are hidden? Because of many reasons, not only because I'm in a rush, but there are many, many reasons and many layers of why people are doing this. And this is a very good way to explain it. The paper is not the scholarship. The paper that we are forced to produce and publish is not the research itself. The research is all of that diagram that I showed. The software, your development environment, the code, all the data, everything that you use to reach that final plot or that final figure or that final paper, that's what the scholarship really is. And it should just have the same value throughout. And because we've put so much emphasis in papers, that's why a few years ago, people started digging in psychology. Why psychology? They were just unlucky. And they were the first ones that were bashed with, there is a reproducibility crisis, but it could have as well been machine learning, medicine, any other science. And since then, we've had so many incendiary headlines saying reproducibility is bad, or science is bad, science is broken. And we've had everyone screaming about there is a reproducibility crisis. Where the truth is, there is a reproducibility chronic problem. And this is because research and the world have changed and they've evolved. But we're still measuring science nowadays as it was measured in 1927. So we still have a few years to catch up. And it gets worse. I know this is a sad picture, and it doesn't necessarily align with the vision that we have with research. And unless you've done research yourself, these are things that probably you would be unaware of. But it gets worse. You might think, okay, it's very easy. You develop your code, you put it on GitHub, attach a license, boom. Everybody can use it. Everybody can reproduce it. It's as simple as that. It's not as simple as that. It's a whole systemic system of barriers for reproducible research. To start with, since we have to publish, there is this bias towards innovative publications. You have to publish new, sexy, exciting research. If you're interested in reproducing or replicating others' studies and proving or disproving hypotheses that have stood for years, then you have less of a leverage in science. The fact that you're trying to make your work more transparent and more reproducible means that you have to spend more time doing it. You need additional skills. The moment that you make your software open, you're going to get questions, you're going to get issues, you're going to have to support users, whether that user is only you in the next 6 months, or your lab, or your PhD students, or your collaborators. There is also a big fraction of researchers that say, why would I bother? I've been doing this way for 10, 20, 30, 50 years, and it works for me. And look at me, I have 500 publications, and 20 of those are in Nature, so I'm good, right? But also, it's because there are very low to non-existent incentives. It seems that for you to make science or research reproducible, you have to spend a lot of time. You have to retrain yourself. You have to convince others. You have to have very tough conversation for very little or no reward, because it's not considered for a promotion. It is not considered as a metric on how good a researcher or committed researcher you are, or how much of an impact your research is making in the world. So it's not surprise that when someone comes and tells you as a researcher, you have to do your science more reproducible, you're going to say, why would I? Because inviting people is not enough. It's not enough saying you have to make your research more reproducible. Not if we don't have the right incentives. Not if our institutions and our funding bodies align with what we're demanding from researchers in science, which is, again, that openness and transparency and collaboration and innovation. Until these values are aligned, it's going to be very, very hard to provide any support for all the researchers to jump on the reproducibility wagon. So I'm going to show some examples because it's all very nice and easy when I talk about the lack of reproducibility, but people are, well, so, okay, what does that even mean? I have 3 different examples of different approaches to the lack of reproducibility. This Excel spreadsheet has become very popular in the economic world and also in those people like me that talk about reproducibility a lot. This Excel spreadsheet was used in a study by Reinhardt and Rogoff in 2013, and it was used to calculate the GDP for different countries. The model that they developed was further used to design austerity measures of a number of countries, including the UK and the USA, back when we had this very big financial crisis. Everybody just assumed that this model and these predictions were right. They were published. They were peer-reviewed, right? So we can trust them. Until a master's student was given the task of reproducing the results of that paper. Because nothing is easy in research, he spent quite a few months trying to reproduce it. He couldn't. And when he had access to the regional data, CSV file or Excel file, it turned out that, if you're not familiar with Excel, when you input a formula and you want to apply it through different rows and columns, you click on the side of the cell and then drag that and then applies immediately to the rest of the rows. It turned out that a good number of rows were not included in this formula, so that dramatically changed the results. But it was too late. When this was done, it was extremely late because countries had already used this to plan their budget and plan austerity measures. So this is a real example on how the lack of accountability and reproducibility can impact the life of not one person, but millions of citizens of the world. This is a very extreme case, and I like to highlight it, not because I'm pessimist and I want to raise these incendiary topics, but this is a very, very sad case of a researcher, the Obokata, that worked in stem cell research. She was one of the rising stars of the area and the student of one of the pioneers of stem cell research. At the young age of 30, she had her own lab, millions of dollars invested in research and in grants because her research was so innovative that it was meant to change not only stem cell research, but healthcare, regenerative medicine, would have a massive positive impact in thousands and thousands of people. Of course, when something is that good and so innovative, you have people all over the world trying to replicate it, and this was not the exception. There were labs all over the world trying to replicate the results, and they couldn't. After years and millions of resources spent trying to reproduce the results, it came to light that she fabricated a lot of her data. She fabricated a lot of her figures during her PhD and subsequently, because she was under the pressure of publishing her thesis, publishing papers for her to get her PhD degree, and obviously to get grants after that. This was, again, if you're in the certain circles, very spoken about, and I don't think this is by no means the norm. This is a very rare and strange case, but it's a perfect example in how the wrong incentives and having the wrong demands or faulty demands from researchers can completely derail that beauty and that transparency of research. And the third example is this. After psychology went all of this storm of the lack of reproducibility, they were held to higher scrutiny. And in particular, this research group in Germany published their paper. Then they were doing an audit on their code and their study to do subsequent research, and they found that there was an error. So they did the right thing, that was retract their paper, but they went beyond that, not just saying, we made a mistake, sorry, we're going to retract this, but also they wrote a very good post-mortem about how that mistake came to be, what they were doing to fix it, and what implications that would have in their further research. But they were able to do it because they had mechanisms in place to do it. They had trained people, they had the skills, they had the support to do it. So these are three very different cases on reproducibility going wrong, and three different approaches of dealing with it. What people don't tell you is that for you to be able to, for example, give a response like in the last case, and reflect back and correct back your analysis and reproduce your own analysis, it's very hard. It's so much hard work. I think by now we've established that reproducibility is good, right? I think we've established that it's something that we should care about. To start with, it helps with correctness. It helps us to spot errors earlier and easier. It also helps us to protect against bad actors, people that are intentionally doing bad things or intentionally fabricating data or figures. But it also helps us to ensure robustness. And this is critical if we're going to then apply for a second or third or fourth round of funding to build on existing work that we're doing. But it also makes it easier to collaborate. Imagine not having practices like version control or data management in projects like the Event Horizon Telescope. That would have been an absolute nightmare, absolutely impossible to work with. But it also enables strong baselines. This would enable us to set a new gold standard of what high-quality research means. It leads to progress. Again, the Event Horizon Telescope is an excellent example in how building on open science, open source, open infrastructure, doing reproducible science leads to great impact of progressive research. Also, it's necessary for extensibility. Again, as I said, if you're going to be building on your research or someone else is going to build on your research, they have something to step onto. And if these parts are not available, people have to reinvent the wheel, which means it takes longer. You are spending much more time, much more money, many more resources in doing the same things all over again. And it also makes you a trustworthy person in the community, in the research community, in the world. So it's time for a cultural shift. It's time that we abandon those practices that we've been dragging for decades and decades, where the number of publications and citations are the gold star for research. And this means supporting open source and open infrastructure, open software, to help with the last mile problem. And I always talk about this because this is the best way I have to explain why supporting all of these additional batteries, like the scientific ecosystem, is important. Imagine that you're in Berkeley, you are that oh, by the way, this is from Chris Holdgraf. He's the best person at putting this kind of examples. So imagine that you're in Berkeley, that's you, the red dot. And your favorite coffee is in San Jose. Yeah, that's where it is. I don't know why. You'll have to ask Chris next time. So to get there, you have three options, right? Walk yourself, pay someone to do it, or use a public infrastructure. If you put this in Google Maps, it's going to tell you that it's going to take you around 2 hours and 12 minutes, and you can take the BART, like a train, or a bus, and then you have that little slot at the end, that little mile. That is the mile that you have to walk on your own. It's the mile that the public infrastructure is not going to help you with. And this is what public infrastructure does for us. It gets us closer to our goal. But it's also what scientific software and open source software and all of our Python ecosystem does. It gets us closer to our goal, whether that is doing reproducible research in physics or in stem cell research or creating secure databases for your users or anything. But we have to ask again ourselves and ask our funders and our institutions, are we making the best use of our public infrastructure? Because so much of the research that is done in the world is paid with our taxes, with all of the world's taxes. So this money is then spent in innovative research, but very little money is spent in supporting and funding these critical pieces of infrastructure that are powering all of the research in the world. And the problem is that it's very hard to quantify their impact because they work well, and they're maintained with a lot of effort and a lot of work. So you know that something has achieved success when you don't have to think about it because it works. And that's why it's so hard to measure the impact of packages like Jupyter or Matplotlib, because they work, but they need still a lot of work. And the last mile is always the hardest. And the hardest of all of this, the hardest part of reproducible science, are people. Whether because we are so into our old practices of I cannot make this reproducible, I cannot make this open because I'm going to lose my competitive advantage, and that means I'm going to have less innovative publications. Or whether because we are gatekeeping and bag shedding what actually reproducible science means. We get so ingrained, you have to write very beautiful, very correct, production-ready code, when researchers are not developers, researchers are not software engineers. In that survey, we had over 50% of researchers developing their own code. What I didn't tell you about is most of them are self-taught, or they learn by themselves. So they're not developers, they're not software engineers. So when you're asking them to look after scientific code and adopt all of these practices, you're adding a second workflow to their already clogged workflow of research, getting grants, writing papers, producing PhD students, supervising research, teaching, going to conferences, and all of the such. So we have these two polars, that is software engineering and research, and we have the researchers and the software engineers at these two poles. When you're asking someone to do both things, they have to do both jobs, and researchers already spend a lot of time doing their work. So one way to circumvent this, and one thing that I've been pushing for a lot, is recognition of folks that sit in between, that have enough good software engineering practices and enough good research practices so they can bridge the gap between these two areas and help ease the load with the lack of reproducibility. And we have to advocate for the creation of career paths, stable career paths for folks like this, because these roles and these needs didn't exist in 1927, but we have these needs now. We need these folks, we need these careers, we need highly skilled, highly trained people to want to stay in academia. That is another thing. We want them to stay in research. And again, researchers are not data management. If we go further and ask them to make their data findable and accessible and open, we're again adding another layer of complexity of workflows. Some researchers are extremely good at this, some others aren't, some others won't have time. But again, research software engineers can help ease the load on a big part of this pipeline. But again, I mentioned that we have to create these careers and create stable career paths, and we have to have incentives for them to want to stay. So people are not only the hardest part of reproducible research, they're also the hardest part of software citation. There is not a culture of software citation. And unfortunately, going to the same problem, citations are the trade kind of research, whether we want it to be, whether we like it to be, or whether it should be or not. That's how it is. And sometimes you have to play the game. Citations are currently the best way we have to endorse someone for a good work, for a job well done. So we should be citing the software we use, whether it's software that you're developing in-house or whether you're using pandas. Probably when you're writing a paper, you don't think about, oh, thanks to pandas and Mark Garcia and all of their developers for doing this amazing job. Because we take it for granted. It just works. It's implicit. But we have to start making this explicit. We have to start mentioning them and citing them so that we have a way to measure how much research is being fueled by them. And here's where initiatives like JOSS or the Journal of Open Source Software are amazing at, because they're giving researchers or research software engineers and developers a platform to transform those scientific pipelines or scientific packages into peer-reviewed, openly peer-reviewed papers that can be further cited. So you're taking that requirement for research, but also it's encouraging the adoption of best practices. It's encouraging researchers to adopt open source licenses and think about how they can reuse and build on somebody else's work. So hopefully now I will have convinced a few of you that fighting this fight is a good thing to do, that it's worth fighting this good fight, that there are lots of things that we can do. Research has gone to a very nice place now. We have a lot of compute, we have a lot of open source, we have very skilled people that are fighting to change research. But what can we do now? What should we be doing now to change research? If you have a lab, or if you have PhD students, or if you're in charge of research, implement checklists and processes to ensure that your research is reproducible. If you can make your data open, that you have processes in place to do so, that everyone is held accountable, so when things go south, nobody can say that they didn't know better. Invest in open tools and infrastructure. Build on the giants that are already out there. Better yet, if you can help them and contribute, or you can convince your institution, or you work at a funding agency and can change things to support this infrastructure, do it. Help everybody make that last mile shorter. Fight the good fight of having new career paths that align with the state of research in 2019. Have new paths that align with what we want and demand from good research. And in general, as a community, we all have to advocate for change. And that comes from probably doing a step in the right direction of making our work more reproducible. Mentoring those others that don't have the skills that you have to make reproducible research. Or just being kind to yourself in 6 months and better documenting, better testing, double backing your data. Thank you very much. And before finishing, I would like to give a special thank yous to a few people. In general, it's the Jupyter community and Chris Holgraf, Kirsty Whittaker and the Turing Way community, and Simon Hedrick and the RSC community and society. They're all folks that are fighting the good fight, and I am very grateful to call them collaborators and friends in this road. Thank you.
Tania's not going to be taking questions, but once she's had a chance to gather her thoughts and her breath, she'll be very happy to have conversations with you throughout the conference. So thank you once again, Tania, for opening up for us with that. We're now going to break out. Our next sessions start at 10:30. Ben is here next with AstroPy, Python on the International Space Station. Then we have workshops in some of the smaller rooms, and talks starting in room D. So just so I can help you, if you don't know already, the Ferrier Hall